Alright, so we've talked a lot about how are we going to code this problem. So now let's actually take a look at some code. This is coded in MATLAB, and let's see here, I'm not a trained computer scientist, so even though I know how code works, I might not have the best coding practices, so my apologies if my coding is bad, but it works, so there you go. Okay, so here let's look at the basics. We have, I should put my keyboard in for this so that I can actually use that a little bit. So let's just start out with degree being 0. And I'll wait to run it until I talk through it. But yeah, so this problem, we're going to run it up until time 1 because that's what's done in the paper. If we look back over, which table is it? Oh, I didn't want to do that. Let's do this. Okay, so we're looking at this table. So this is at time t equals 1, right? Table 1. What are we looking for? We're looking for table 1. In each table, the L2 norm of the errors at the final time t equals 1 are presented. I didn't compute either of these two errors because this one is sort of weird because you'd have to like compute projections and stuff. I don't want to do that. And this, I mean, I don't want to do that either. This is really all we care about because, well, I mean, I guess it's not, but it's sort of what I'm most concerned about because I want to know how well this code runs. And so I want to know what the actual error between the exact solution and the computed solution is. Okay, so L2 error, this is for space P1, so K is going to equal 1. I'll show K equals 0 just to show what it looks like, and we'll do N equals 10. So anyways, this 100, that's the constant, and this nx squared is going to be h squared. It's a little confusing. Don't worry about it. Just basically trust me that I've implemented this the way that's done in the text. Okay, so we start with u and q. These are going to be our vectors, and so the way it's set up is each vector, each column is going to be a discrete time point, and the rows are going to be the coefficients, and it's set up like the vectors that are shown in my write-up. Okay, we're going to need to do some computations involving sine and cosine. So instead of using sine and cosine functions, because we have to do things like multiply them by other polynomials, the easiest way is to actually write them out as polynomials. So that's what I'm doing here. So I'm taking sine and cosine and expressing them as polynomials using their Taylor polynomials. And I'm going up to degree 30. That's probably more than necessary, but I did notice that if you go with degree like 10, then that's not enough. Okay, so we want to build our matrices that we use where? We want to build the matrices that we see. No. And there. These matrices. We want to build these. So this block of m's is going to be called m block. This whole big thing here is going to be block 1, and this thing is going to be block 2. Nope, I did not want to open that. Thank you, Acrobat, for being there. Please stop. Okay. Why do I even have that? I don't use that by itself. Okay, so that's what you see block m, block 1, and block 2 are. Now we got to make the other matrices first. And these, if you go back to the text, these are just like up here. That's exactly what these are. But before we get there, we have the polynomial basis. So remember what our polynomials look like. You take x minus xi over delta x and raise it to the power of I. That gives you the ith element of the polynomial basis, going for I equals 0 to k. So the first row is just going to be 1. And then in order to get the next rows, what I do is I take the previous row and multiply it by this polynomial. And the way I write the polynomial is in this form. And this is how MATLAB deals with polynomials. It writes it as a row vector, and the vector most to the right is the degree 0 coefficient. Then this is the degree 1 coefficient. If this had 3 entries, this would be the degree 2 coefficient, etc., etc., etc. And convolution allows you to multiply polynomials together. So if we want to take convolution of the polynomial, let's say x plus 1, and let's see, if we multiply, if you take the polynomial x plus 1 and multiply it by x, say, which would be 1, 0, then we should get x squared plus x. And so when we do this convolution, we get x squared plus x plus 0. And so that's x squared plus x. So yeah, so to raise this polynomial here to the power of I, we just, for each row, you take the previous row and multiply it by this polynomial, and that will raise it to the correct power. Now, of course, there will be zeros missing at the end here. So like for the first row, instead of having just the polynomial 1, you want like 0, 0, 1 for k equals 2. And so you have this thing to put some zeros in there, and then you're good to go. That's your polynomial basis. Yes. Guess worth noting is that this 1 over dx minus 1/2. So this is, you're finding the polynomial basis on the first cell. But it doesn't really matter because these things are translation invariant. The integrals anyways. So for m, remember we have the integral of phi m phi l on this cell. So you have to do this weird thing where you have to use this convolution to multiply the polynomials together. And then you have to take its integral and evaluate it from 0 to dx. So you evaluate it at dx and then subtract it evaluated at 0. And so that's what this all does. It's a little messy, but you can parse through it and see what it does. Also note how I'm dealing with the m and l plus 1. I'm letting m and l start from 0 and go up to k, but then for the actual indexing, I need to add 1. And then down here, I don't need to do the L minus 1 and M, or I don't need to do M plus 1 and L plus 1 like I did in the write-up, because I just did it this way. I did it this way because I was like troubleshooting and I was getting confused, so I decided to do it this way and it worked. I guess I could go back through my write-up and make it consistent with this. It's not a big deal. Anyways, we've also got G. G is going to be used in the initial condition right here, I believe. Yeah. Because G starts out being the same as the matrix M, but then the final row you change it to this thing, and that's exactly what G is here. And then you use I and P. So, you know what? I'm actually going to run this here with k equals 0, t max equals 1, x max equals 2. We're just going to see how this looks. Not only do I solve it, but then I use some things to be able to, at the end, to be able to actually plot it. And it will actually come out as a movie. And hopefully it comes up well on the video. And it'll probably come up better now than later, because my computer will probably be very static later and not picking up all the frames. So anyways, let's see what this looks like. This will probably take longer. I didn't think about how much longer this will probably take to run. But yeah, look at that. So the blue is the approximation and the orange is the exact solution. And you can see, especially at the beginning and even for later times, each of those horizontal lines is a distinct cell, and you can see that matches up with the orange curve almost exactly. And in fact, it does match up exactly at the very first time, and that's because of the fact that we are, remember the projection, we had this special projection that we were using to make sure that it agreed at the left endpoint. And that's exactly what we see happen here. So that's nice. But yeah, I wanted to do this just to get some of these matrices. So if we look at what P and Q are, so we're using P and Q to construct these block matrices. So if we look at P, oh, well I guess I only use P and P prime. So P looks like this. So you've got ones off the diagonal lower, and then you've got this one up here in the corner. If you remember, that's exactly, if you look at the matrix equations, that's where this B times C term comes from. So what we're going to be doing is we're going to be using that matrix P in order to tell the program where to put B times C, the blocks. And then, and of course, A minus B will just go along the diagonals. Now for B times E, which we see in the second equation, that goes above the diagonal and also in the lower left-hand corner instead of the top right. But if you look at that, that's just the transpose of the placement that we had before. And so we use P prime. And that's what these functions do. So if you want to make a block matrix, this cron something, this is some sort of tensor operation thing. But basically it takes I and it replaces each element of I. So what cron of the first matrix and the second matrix does is it takes a second matrix, and for each coefficient in the first matrix, it replaces that coefficient with that coefficient times the scalar multiple times the second matrix. So in order to get the dimension, you actually multiply the dimensions of the first two matrices. Multiply the rows together, multiply the columns together. Because each entry in the first matrix becomes a multiple of the second matrix. And so what this is going to be is, so this I is the identity matrix with nx entries on the diagonal. Nx is the number of cells. So for each cell, we get the matrix M, and M is a k plus 1 times k plus 1 matrix. So this matrix itself is going to be k plus 1 times, it's going to have k plus 1 times nx rows and k plus 1 times nx columns. And it's going to look exactly like the matrix that we saw before, right here with the m's along the diagonal. It's exactly what this is. Then here, again, we put a minus b on the diagonal, but for p, so below the diagonal and in the upper right-hand corner, we put c times b. And here I'm using dot times because, like I mentioned before, I'm multiplying these matrices together element-wise. And then here we've got similar thing for block 2. It just matches exactly the text. Okay, y0 and y1, I don't think I use these. I think these are from a previous iteration of the code. I don't use them. Okay, so now we're actually going to get into the actual solving the values. So we're going to take J is going to range over all of the discrete space points. And we're going to take care of the initial conditions manually. So if J equals 1, then for each cell, for each n equals 1 to nx, we're going to get the coefficients in that cell. So we first have to construct the polynomial basis, which I do like before. However, note that I'm using minus n plus 1/2 here. And this accounts for the fact that the polynomial basis needs to be translated to the right for each cell. And other than that, it's the same way we did before. And then to do this, what we do is we just calculate the so the u coordinates, the coefficients that are being stored in the matrix U, are going to be G inverse times H. Because here, if we go back to this thing here, we've got this matrix times the u values equals this matrix. So this matrix on the left here is G, and this matrix on the right here is H. The matrix G we constructed at the very beginning of the code. H needs to be constructed for each cell, because this integral over ij of sine of pi x is going to change with each cell. And so this is going to be, we compute this integral using similar techniques to how we computed that matrix M. However, again, we have sine of pi x. So that's why we're using polysine here. Remember, that's that vector that we have, which is the polynomial form, or the Taylor polynomial for sine. And we're using that here because we need to multiply it by the polynomial basis function. And then we evaluate that at the endpoints after integrating it. And then, of course, you have to adjust that final entry of h, and you just evaluate sine at that particular point, as we saw. And yeah, that's how you get the u values. And then you can get q directly from that. So that's how you take care of this. That's how you take care of the initial condition. Now we move on to the second point. This is the other one that we had to deal with manually. And now we just we build a polynomial basis again. Now the next thing we do is we create the polynomial for u, and we do it in the standard basis. And that's literally just, if we go back here, that's computing where is it? This thing. It's just computing this, UH1. It's just computing this on the right-hand side here. You take the, I think I described it later on. I don't know why I don't see it. This, yeah. You're just doing this. UH1 equals blah, blah, blah. You just compute this. But again, once you compute that, you get it in that vector notation that MATLAB uses to store polynomials. And it's not you need to extract from that the coefficients for our polynomial basis. And so that's what this weird chunk of code is doing here, this if k greater than 0. So this is really weird. Oh wait. No, this is still in the phase where you're constructing the polynomial itself in the standard basis. And that's why we're taking p is starting at 2 and going by gaps of 2. It's because you're only dealing with the even derivatives of this. Remember, we have to only consider even values of n. That's exactly what we're doing here. So this is how we're summing it. Okay. Then you have to change from the standard basis to the finite element basis, which is much more confusing than it looks here. And you just do this procedure that I described here. And there's two confusions. First of all, you have to do that conversion, which in and of itself is difficult. The second thing is that the way that u is constructed is that as you go down in the row numbers, you increase the degree of the coefficient. So the first entry will be for the degree 0 coefficient. Then next you'll have the degree 1 coefficient. Then next you'll have the degree 2 coefficient, etc. The way that that MATLAB stores polynomials is, if you remember that that vector, it looks more like how you would write out a polynomial, but it's more difficult to deal with mathematically, because the first entry of that vector is the highest degree term, and then the next is the next highest, and then you go until you get to the lowest term, until you get to the degree 0 coefficient. And so it's backwards. And so you see a lot of weird, like, s goes from k plus 1 and you count backwards, and there's it's a mess. But you just figure out how to do it, and then you do it. And then once you do that, you have all the coefficients for u, and that's how you get u. And then q is really easy, because you just do that matrix thing. You take this block 2 that we have, and you just use that to find q, because remember, this block m times q is going to equal to that block 2 times u. Then finally, the part that looked the most complicated in the write-up is the easiest thing to write here. Because I guess if you include the writing of these matrices previously, then it's not necessarily the easiest. But for the induction step, it's really easy. So if j is 3 or higher, then you just do these matrix operations, and you multiply by u by the previous column, 2 columns ago, and then you have to involve q here. Then you have to solve for q in terms of u, and you're done. And so that's how you do it. That's how you get the coefficients. So if you actually look at the matrix U, it gives you all of the coefficients. And so then we want to plot it, and so don't worry about this too much. So let's see here. So what we have to do is I do something so that we only plot it if because I don't want it to plot too frequently, because if it plots too frequently, then it's going to go ahead and take a long time. But I also like being able to see these things move around. I think that's one of the things that I enjoy about this topic, is that you can run these simulations and you can make movies out of them and you can watch them. I think it's really neat, and it's really neat to be able to have this tangible result. Something that you've actually created. But anyways, so what we have to do is so I have some gaps to make it so that you don't plot it every single time. So that actually looks like a movie and not just not something that moves very slowly. Anyways, so at the same time, I also want to compute the error. And computing the error is difficult because you can't just, typically to compute the error, you compute the L2 error, meaning you take the functions and you just compute the L2, you compute the L2 error. The way that I'm doing this to make it a little easier, but it's also tricky, and to also make it take less time, is to actually use Gaussian quadrature. And quadrature? Something. I don't know. You can read about it, but basically instead of integrating the product of these two functions, because you want to integrate the let's see, so this is the L2 error, so you want to take the difference between the exact solution and the approximate solution, square it, and integrate it, and see what you get. That's your L2 error. Oh, but at the end you take the square root. But yeah, so once you do this, you once you do this, just lost my train of thought. That's not great. So instead of computing this, the way you compute this integral is that you just choose a number of points in the space you're integrating over, evaluate the function at those points, and then sort of take a weighted average of them. I mean, it's basically the same idea of Riemann integration, but it's like, how efficiently can you do Riemann integration? Oh, speaking of Riemann integration, I forgot to mention something earlier. Way back when I was talking about doing derivatives with the second time step, there was a little bit of I was moving derivatives around. And if you're a pure mathematician, you might have freaked out like, you can't just move derivatives around, you need to use Fubini-Tonelli. Well, the nice thing about working in numerical analysis is that pretty much all the stuff that we're doing is compactly supported, and so any function that's continuous automatically becomes uniformly continuous, and so it's really easy to, and like, as long as you don't have any blow-ups, which you really can't in a computer simulation, or else it doesn't work. So everything is going to work nicely, and you're basically always able to do Fubini Tonelli, because you never have to deal with blow-ups, really. But anyways, yeah, so so interchanging those derivatives the way that I did back then was fine. So don't worry about it if you were. But yeah, so anyways, coming back to this, so we use Gaussian quadrature to approximate the integrals, and that's what we do here. It's a little confusing. And then we also obtain plotting data. So what I do is I go through and I sort of take each interval and break it up into a bunch of different pieces, or I sample a whole bunch of points from each cell and then evaluate the function at each of those points. And so that's how I was able to get that plot that I got. And so anyways, with how long this video is, I'm sure that if I try to run the function now, it's not going to show up on the video at all. So what I'm going to do is I'm going to stop this now, and then I'm going to do a final video where I actually run this for a few different values of k and nx, and I show you how the error performs and show you that this works nicely. So yeah, that will be the next video. But as for now, this is how you code up a finite element method.